So, good morning, class. I hope you see now my screen. So, yesterday we discussed about what is electric current and how does how can we create electrical current from the diversion of the electrons from high potential or high potensity to low concentration of electron gradient. So that is using our voltage or our battery cell. And today we're going to talk about what is electrical resistance and Ohm's law. This pertains to the electric discharge after the movement of electrons from our source of energy or our battery cell, for example. So, what is electrical resistance? This was the main interest of German physicist George Simon Ohms. In 1800s, he published a paper entitled Mathematical Measurement of Electrical Currents, which describes how current in a wire responds to a change of voltage in simple circuits. When we talk about simple circuits, ito yung we have their battery, then a length of wire, then let's say you have their simple light bulb, and that is close to another end of the battery cell. So, okay, so this is an example of the relation of the resistance to voltage. If you have there certain volts, that is directly proportional to the amperes and to the resistance of the wire. So for any set of trial, Ohm observed that voltage current ratio is constant for the wire. He called this wire's resistance electrical resistance, or voltage is over current is equals to constant, or the electrical resistance. And he further he created what we call this Ohm's law, wherein voltage is equals to the product of the current and our resistance. This is where V is equals to voltage in volts, I is equals to current in amperes, and R is resistance in ohms. Now, talking about resistivity of certain electrical copper, so we have here resistance is both an intrinsic and extrinsic physical property which depends on several factors. It includes the length of the wire that we have, the cross-sectional area, the width of that, what is the shape of that width, merong flattened, merong circular, and we also have the kind of atoms composing the wire. So there are different conductive materials with different kind of atoms there. So depende kung anong material nun, no? So the kind of atoms composing the wire, this is called the resistivity of the wire. There is specific resistance depending on what material that you have. So resistivity is the specific amount of resistance offered on a unit length of wire. So from Ohm's study of resistance, resistivity P is equals to big letter A over our J. So since V is equals to ED, no, then J is equals to I over A, then we can create that P, the resistivity is equals to VA over ID. But we have their voltage is equals to IR according to Ohm's law. Hence, we can create resistivity is equals to P big L over A. Now, ito lang yung pinakita niyang paano niya na-create tong formula to na written in red. No? So, R is equals to resistance of the wire in ohms. Um, I think uh, it resembles letter P, no? That's why I read this as letter P. So, resistivity of the wire in ohms, and this is L for the length of the wire in meters, and A across section of the wire in meters squared. Temperature, this is because resistance dissipates electrical energy. It is thus manifested as a heating effect in the wire. So external temperature may affect it. This is the basis for constructing thermistor or thermometers which read temperature using wire resistance. So the effect of temperature on resistance varies. So including the metal conductors. So there is a direct proportion on that. In semiconductor, that is inverse proportion. And in superconductor, it offers no resistance at very low temperature. Okay, so this is the resistivity. The resistance temperature relation is described in this equation. This is where is your final R is equals to the final resistance at temperature or big T in ohms. R sub O or 0 is our initial resistance at the temperature T in ohms. And big T is our final temperature in degrees Celsius. And T sub 0 is equals to initial temperature in degrees Celsius. Then our alpha is the temperature coefficient of resistivity in every degree Celsius. So this is the remark. So the temperature coefficient of resistivity is a constant for specific material. So and it describes the amount of resistance change per degree centigrade rise in temperature. So negative temperature coefficient resistivity indicate a decrease in resistance as temperature rises. Positive values indicate an increase in resistance per unit rise in temperature. So the former is acquired by semiconductors while the latter is acquired by ordinary metal conductors. So resistivity at room temperature is multiplied by 10 raised to negative 8 ohms in meter. Okay, so I have here a table showing resistivity of these different materials at room temperature. Okay, so you have there, for example, silver for 1.447 and mercury for 95.0. The next one is about electrical power. We are done with the voltage, the electric current, and the resistivity. Now we're going to talk about what is electric power. Now, in electric power, power is generally defined as the rate of doing works or the rate of energy supplied or consumption. So your power is equals to the work exerted, or it stands for big W, work or energy in joules. So over time in second. So in a simple circuit, it composed of a battery whose terminals are connected in series in series with a single resistor. So the battery performs work on charges and it is said to output power to the circuit. So the resistor opposes the flow of charges and it is said to dissipate or waste water. So our resistor input, the power. So the general electric power equation is equals to P is equals to W over T, but they have their work, it's equals to Q multiplied by the voltage. So we can create this another formula that power is equals to voltage multiplied by the current. So this is the unit of electrical power, volt ampere, or can be in watts. So power output of a source, an ohmic battery or cell obeys Ohm's law. So the power output of the source is equals to the voltage multiplied by the current. So you have their terminal potential in volts for big letter V and I for current output in amperes. So the power of a pure resistance. Note that ohmic resistors have their power given. So P is equals to VI, but our voltage is equals to I multiplied by R or resistance. So we can create that power is equals to um, IR, open and close parentheses, multiplied by another current. This is equals to I squared multiplied by our resistivity. Or we can say that this is P, or power is equals to V over R multiplied by V, or we can say that power is also the same as V squared over our resistance. So these are different formulas using different given units. So pwedeng ang given is current or resistance, or pwedeng voltage and resistance. So it must be shown that the unit of I squared R or V squared over R is also our wattage. So since resistor absorb electrical energy from current as electrons collide with their atoms, their temperature increases. So thus they are characterized by a maximum power rating. So which is the maximum power that can be dissipated without overheating the device. So when this exceeded, the resistance changes or worsen, then the device may melt or even explode when it exceeds. Okay, now when we go to power consumption, companies that produce electricity charge consumers in kilowatt per hour. This is a unit of power multiplied by the time or the work. So thus we pay Meralco for the work they do in producing electricity. So a typical monthly electric bill carries generation, transmission, and distribution charges. And hindi lang itong tatlo, kundi meron pa yung iba. Let's say yung system loss. Yung system loss natin, yung mga nanakaw na kuryente ng mga nagja-jumper, or even yung mga nawawalang kuryente during transmission. Kasi kung ano yung amount ng electricity na na-produce ng mga ating electric producing companies, hindi naman yun yung exact amount ng electricity na marireceive natin papunta sa mga residential places, yung mga commercial establishments, nababawasan siya kasi as it travels along the wire. So, yon kinocompute din nila yan at binabayaran din natin yun kahit yun ay tinatawag na system loss. So, there are still government taxes and universal charges which were not included. Pero ito yung iba pang sinasabi, yung parts ng ating Meralco. So, kung makikita nyo, yun yung ating generation charge. So, meron dyan computation. Let's say you have there 415 kilowatts per hour. So, yung price niyan, kada per hour is 4.5090 Dow. Then, if you will multiply that, ito yung amount, no? Then, in other charges, transmission, system loss, distribution ng Meralco, at subsidies, ang magiging total energy amount natin is amounting to 3,000. Okay, so ito yung example mo. Now, this is the end of this video discussion.